Yeah. Okay, hello everybody. Welcome to the afternoon session. We're going to kick off with our first talk of this block with Casey and Sebastian talking about array dispatching in Python. So I'll give you 25 minutes. Please save any questions for the end.
Hi, I'm Sebastian, and we are going to talk about different approaches that different projects in scientific Python ecosystem has taken, dispatching approaches. So here's a little bit about me. I have been working on these scrums or programs and these open source projects and these communities. I have been volunteering on these things, and there you can find most of my work, and that's my username as well, and that's my profile in most of the places. So this is going to be the contents, and it's like I tried to pull it off, but let's see. So dispatching in a very general sense is like going from point A to point B, and how do you reach point B by some delivery address information. So in programming also it's kind of like that, but you are taking a function call from the user and sending it to another library, and the address is like an attribute of the function or the argument types, or maybe a global environment variable or configuration or something. And but yes, why do we do this? So maybe this library B has like fast implementation of the same algorithm, or maybe it supports another type. Or maybe like its API is not that simple, but library A's API is like simple. So, or it's like maybe this library B1 is used in our ML workflow or HEP workflow. So now how exactly it's done? So I'm going to just give a dummy example. So let's say library A has like a simple add function, and there are like four. Now just a disclaimer for next few slides, don't look at the code, just listen to what I'm saying. So there are like four steps. Like first you get the name of the backend package, and then you import it. Then you import it, and then you like convert the given arguments into something that library B can understand, and then you just find the add function inside the library B1 and call it. So, but can we like make it more general, because there are like so many if else conditions, and maybe we can like give some of the responsibility to the library B1, 2, 3, 4, and so for this step, I'm going to go and let this order 4, 3, 2. Okay. So here, what I've done is that library B1 offers a namespace, and we get like all the functions in that, and all the functions have like unique names. That's an assumption, and then we just call that add function, and for convert you also say that you take in the function name and arguments name, and you only library P1 you only give us the correct argument types. And for importing I just used the tender, and now you can see that in these if else condition the code also became quite general, so we can like remove all these if else conditions for other libraries. And yes, when you remove it, it's quite small. And here, like you can see the step 3 and 4 we have delegated to library B1, and but maybe we can make it even smaller by putting this logic, this if logic, into a decorator. And so now all you would have to do is like put this underscore dispatchable decorator on all of your functions. So now we're going to look at how this dispatching is actually implemented in different projects, and Sebastian is going to talk about NumPy and LAPS.
Yeah, so I'm Sebastian. I'm working at Rapids, and I'm working also as a maintainer of NumPy. And NumPy has a little bit of a, like we saw this if-else approach in a sense that just hard-code it and then generalize a little bit from there. And NumPy uses more of like the Python operator approach. And I wanted to walk through that a little bit. So NumPy started with array ufunc, I think around 2013. And it took a few years, and it was first just for a subset of the universal functions, with like the simple math functions. They are all structures very similar, but that's of course not enough. We want to cover almost everything, and that happened then with array function, and that's what I want to show. And the use cases in sample are actually everywhere. There are so many libraries I can't list them all. But Dask was AstroPy units has the NumPy array of meters concept, and a lot of other projects do. But AstroPy was involved early on in it, and we allow this. And Dask arrays, distributed arrays, integrate into NumPy or can be used with NumPy, CuPy, JAX, CuPy numeric. A lot of those projects do that. The usage, I think there are kind of two use cases why we want this. We have the more AstroPy units use case where the user actually just doesn't write AstroPy unit.mean, they just use numpy.mean directly. So you're like a subclass which integrates deeply into and looks and feels like a NumPy array directly. Then you have the CuPy or Dask use case where you do often have your own API, but you want to integrate, and it's nice to be able to kind of swap it in. And I want to give a brief example, which is for this like, simple mean. This is very small. So I use import NumPy and CuPy, import it. I define my silly little mean subtraction thing, create some data with it, and of course, if I run this on NumPy, I get back a NumPy array, and sorry, this is very slow somehow. Good. So it returns a NumPy array, and if I do the same thing on a CuPy array, it'll come. Then it will return a CuPy array. And so this is now a CuPy ND array, so I passed in a CuPy array, I got back a CuPy array, nice. And I can check that the result is basically the same. And that again uses dispatching because you have NumPy and CuPy, and NumPy does not understand CuPy, but the NumPy all close returns true anyway. And why would we do this? One reason, of course, why we use GPUs is always that it's fast, and I can run it with the CuPy array here and the NumPy array, and you see that on the CPU it took, in this case, 7 milliseconds, and if I look at the GPU down here, it took, I don't know, 430 microseconds, so it's much faster on the CPU. But how does it work internally? With the NumPy, yeah. It's basically inspired by the Dunder approach from Python. So if you have a class and if you have add and the operators, the binary operators in Python, they have add and radd, and they return not implemented. So it kind of works the same thing. It's inspired by that. What happens when you call np.mean, NumPy will figure out all the array arguments that come in, which in this case is just the CuPy array. And it checks if this array function Dunder exists on it. And that array function is a method on the class. And if we look for all the arguments, we look if it exists. Then if it exists, there's a bit of a more complicated step where we find the unique ones and deal with subclasses, because if there are subclasses, things get a bit tricky. But then you end up calling the array function directly. And the array function is passed the function of NumPy, in this case np.mean, and the types, all the types that are involved. In this case, it would just be a CuPy ND array, and then CuPy can go through and say, well, I know np.mean. If it does not know, it can return not implemented to tell NumPy I can't execute this. And then it can go through the types and say, CuPy understands NumPy arrays in this case, and it understands CuPy arrays and subclasses. That's what the choice is. And if you would pass in a JAX array, it would say, no, I can't do this. And otherwise, it just returns its own internal function then. And the real code is much the same. It's just a little bit more complicated, of course, with the lookup. But it's really not much more complicated. And this allows very nice interoperability with NumPy. As such, it's this binary operator approach, and it's adopted by a lot of objects out there that support this. So if you have things, you can interoperate with NumPy very nicely often. And I think generally this is a great approach. If you are in this position of having an object and you want something like a subclass, like AstroPy, a subclass from NumPy, then I think it's a great approach to achieve this, honestly. However, there is this bit of an adoption problem in that one thing is, for example, Torch never adopted it. Maybe that's part of the reason. Libraries like SciPy do not use this to allow you to pass in a Torch tensor or a JAX tensor and work with that. Maybe smaller libraries do, and if you write your own code, you can use it. But bigger libraries never adopted that. And that led us at the one time to discuss NEP37, which was the idea to do it a bit differently. In this case, I just gave the array API compat because I think that's, but a lot of people would have been at the talk. The way to get it is you pass in array API compat array namespaces, you get all the arrays that you want to work with, pass it in, and then you get back XP, which is a namespace, and it could be NumPy, it could be JAX. And the nice thing about that, if you're a library, you just do it once. You don't have to do it over and over and over again. You have like this XP object that you can understand and reason about very nicely instead of dispatching every single time when you interact with NumPy. And this is very actively adopted into SciPy scikit-learn, and if you're working with arrays and you want this to achieve, you should totally look into it. If you say, I'm not working with NumPy, I work with data frames, then you should look into Nabats, which is a bit different from a philosophic, I mean, it's the same thing, but it's a bit more complicated because data frames are more diffuse, more different. So there's a little bit more to it. Yeah, and that's one approach to dispatching. And I want to hand back to Aditi, who is talking about NetworkX, because NetworkX adds a little bit extra on top of that.
Hi, so what is NetworkX? First of all, it's like a graph analysis library. So these kind of graphs, these are also called networks. So you basically have these circles, and these are called nodes, and there is data in that. And two nodes have some sort of a relationship, and so they have a line which is called an edge, and these can be anything. So in NetworkX, the need for dispatching was mostly that we needed it to be fast because it's pure Python, but we also don't want to change that because it's simple and easy to use, maintain, contribute, and also like there were a few like subsets of algorithms, like packages that were implementing the subsets of algorithms. So it was also a kind of way to create an ecosystem and offer a nice user interface, because sometimes people would just use a different package to run one function because they needed speed. So first step is also like how do we get the backend name over here. So there's so I've just like done a setup, like installed the backends and turned on the GPU because we are going to use the GPU backend, and so NetworkX has a very simple API. You just create like a graph object, and then you add nodes and edges, and you draw it. You get the graph. And betweenness centrality is basically, it tells you how in between a node is. So Okay, yeah. So you can see like I've created a big graph with like 1000 nodes, and like because it only has 2 CPU cores, I had to only limit to 1000. So if you run it like normal network X function, it takes around 84 seconds, and over here you can see between the centrality is like highest for one because it's most in between. Okay, so now it's like our dispatching setup. I'll show just one example and not show all types of dispatching. So this is like here we are importing cugraphs, and then we are creating a cugraph from a network X graph, and then we are just passing a cugraph into a network X function. So it should run quickly. Okay, so here you can also see that it's dispatching to cugraph as login messages, and it only took like 2 seconds instead of like 80 something seconds. And you can also like pass out backend priorities. So GraphPlus does not implement between the centrality, so it will fall back to Xcograph. Okay, so this one I have just passed, like you can also pass like backend is equal to cugraph and it will run, and it's saying that it is caching the graph, and next time it should give a warning saying that you are using a cached graph. Okay, let's just move on. Okay. Yeah, so this is the big warning that you are using a cached graph. So these are like the 4 ways that I was going, I kind of showed. So like first one, this one is like type based, but like the cugraph object has like a network X backend header which stores the backend name, and these 3 ways you are just the user is directly getting the backend name, and there's like one-on-one mapping for between backend and types. So but now, how do we like find the backend just by name? So we use something called as entry points, and entry points are usually used to like extend the functionality of the library. So like you can think of this is a boring analogy. So like the main function of a vacuum cleaner is to clean, and you can put different nozzles on it to create like a specialized functionality. So I think Napari has it, or they talked about it, and dispatching is just like exploiting entry points to the max. You are just saying that, just change the whole machinery inside the vacuum cleaner, we don't care. So this is how you define an entry point. You have a group which you can use to group all the entry points, and you can get all the installed backend. I'll try to like show it. It's like pretty simple to, you just have to like run this import lib, and you get all the backends. So and the name of the entry point is backend name, and we either get it from the user or from the type, and backend interface namespace is a namespace of all the supported functions and the convert functions. And so here's like an overview. You get all the backends from entry points, get the backend name from user, and then you get the namespace in which all the algorithms are, and then there's also like Cameron children, you can skip this, and then you convert the graph if it's not already converted, and then you call the backend implementation and you convert the output if needed. And in scikit-image there is the main object is numpy arrays instead of a graph object, and you cannot like modify it because it's not owned by scikit-image. So type-based dispatching is a bit difficult, but that's the goal. And like API standards, it's hard to adopt because of its size and heavy nature. And one possible solution is Spatch, and Sebastian is going to talk about.
Yeah, we don't have a lot of time for talking about Spatch, so I just want to very briefly. The idea was to take the lessons learned from NetworkX and from also the tries in scikit-image and try to figure out how to do dispatching in what we need in the ecosystem and make a library that either is a blueprint or something that we can base on. And the idea is really to have recognizable API for the user, and I think that's still something to work on and establish. And have a few principles, like I would like an entry point space for documentation and for introspection. I would like fast type dispatching, but also this named backend selection, which seems to be useful in NetworkX ideally. And maybe the key point is the library should not have to do much besides adding decorators to their functions. The backend should have to do a little bit more work and define their entry point, but we would always use strings and then just basically force you to say which types do I work with ahead of time so that Spatch can do some magic to make it a bit faster. And then for the user, it should be, if you just want to use CuPy, you should just be able to use CuPy, but if you need this additional things, we provide you with the context or other options to do that. And if you're interested, then it's very much usable already, but I'm sure that we will develop it a little bit and go from there. So maybe to summarize the different approaches, we have seen the initial approach with np.main, where we have the dunder method, this magic method, like Python operators. Then the array API, which is this library-focused approach, where you get the namespace and then you work with the namespace. And that is not so much. I always think it's not end user because the end user just wants to write the same functionality. But if you write a function, then it's very nice to be able to do this XP. And you should and can use this and try it out in SciPy, for example. And then beyond that, you add this dimension of where NetworkX has on the one hand has this dunder, in a sense the same approach with the backend name, but on the other hand has these options where the user can select and do priority systems. And then the entry point system, and that is a very nice way also to have documentation. If you go to the NetworkX documentation, they actually have backend supported by this cuGraph and whatnot, so you can see that, and you can, at runtime, you can see, oh, these are the backends as Aditi showed. And then with Spatch, I would like to go basically much the same as NetworkX, but maybe go one step further and make it possible, because this NetworkX approach does not fit for scikit-image, and hopefully make it that we can solve the use case like scikit-image with a library that we can agree on, and that can be Spatch, or maybe it's not. But the thing is that for me with Spatch is that it's much harder than you think it is to get this right. It's kind of simple in many ways, but then there are a lot of weird corner cases, and we would like to make it fast, so move it to C. So and those things I could do in Spatch or in the library, and I can't do otherwise easily. And as an overview, maybe I mentioned most of the things. We have the entry point, no entry point. Array API is kind of different in the sense that it has this focus for libraries. You use it when you write a function. You don't use it in a script. And then Spatch would be And one thing that stands out in NetworkX that it does conversions, and I'm not sure about Spatch doing conversions yet. I kind of lean towards backends doing conversions, but that is another one. Well, with this, I hope that you have some enticement to either use it as a user or to discuss how to integrate it into libraries and gotten a bit of an idea of how you can approach this problem. And with that, thank you for your attention.
Great, thank you very much. That was an excellent presentation. We've got 5 minutes for questions. I'll run around with the microphone to people with questions if you can answer with that one, just for the recording. So yeah, first question.
Hi, thanks, really enjoyed the talk. When I look at the kind of Dunner methods being defined, I get that there's a need to kind of like say, okay, this is different to just a regular method that we're attached to as class. But I guess when I think about Dunner methods, I think it's a reserved namespace for core Python. And I know that from the naming I see there is like effort to say Dunder NetworkX this or Dunder array this. I'm just wondering like what concerns you have with maybe perhaps smaller packages like adopting this approach.
Yeah, good question. I'm not sure whether we should be using Dunder quite as much as we are doing it, to be honest. But I'm always with array ufunc and array function, for example. I feel it would make more sense to call it numpy ufunc, numpy function in a sense. We just as a numpy we have a lot of history, I suppose, to use this. Just feel like we are the array, but I guess that's not really great. I don't know. I would hope that if you have a long like a package name, it's kind of clear that there's not going to be clash. And I think Python is also a bit careful when they introduce to actually check if someone is using it. But if you have an idea of not using Dundas, then
That's what it is.
Any more questions? No? Perfect. Okay. Well, thank you for coming. The next session starts at 5 past. Yeah, enjoy the rest of the day.
maybe you should have done that.
Yeah.
I think. Awesome. You're right. How do I see your name? Mikhail?
Yes.
Perfect.
More or less, I'm worried if my PC will survive. I can unplug this, right?
Yeah.
Or do I have to?
Well, if you've got HDMI, just pull it out. You'll be fine. You won't. You need that for the clicker if you want the clicker.
I have a
but
clicker of mine.
if you have a clicker, then you'll.
Okay. That's my screen. I don't have a screen here though. So, okay. Let's quickly fix that.
Masz czas prezentację?
Tak.
O, fajnie.
Tak nie powinno być.
To taki dziwny. I think the big green może tam będzie coś. Widzisz. Co mówię na godzinę? Apply. Yo, magia. Działa wszystko.
Aha, teraz nie, bo ja teraz jeszcze wiem co.
A, musisz
Bo ja chcę jeszcze zrobić edit arrangement, żeby mieć dwa ekrany, zrobić apply, zrobić keep. No.
No super działa.
Teraz mogę zabrać to do góry, albo gdzieś. Tam mogę.
A my tutaj w dół.
A na ekranie? Jest taka szansa? Nie? A, nie, w górę działa. Teraz znowu
Mogę pytać będzie mikrofony, ale to będę potrzeba ich wszystko chyba słuchać.
Ale do nagrania jest potrzebny mikrofon?
No nie, no tak, ale żeby, jak ludzie będą mieli pytania, to chyba sobie poradzą bez mikrofonu.
No fajnie było, że jednak żeby rozmawiać na nagraniu do tego, żeby wiadomo było o czym mówię.
No dobra, fair enough, tu usiądę gdzieś z przodu i postaram się ludziom podawać.
Ja mogę powiedzieć z mikrofonem.
Nie, ale ja mogę wziąć ten mikrofon i podawać. Okay, so I'll introduce you, and then you've got 25 minutes, invite for questions. I've got some little signs I'll hold up and show you kind of how long you've got. And then at the end we'll use the microphones for the Q&A. Hello everybody, we'll get started on time. We will give a warm welcome to Mikhail, who's going to talk to us about number and MPI, combining just-in-time compilation with multi-threading and distributed computing. So please, round of applause.
So many thanks that I was given the opportunity to give this talk by the organizers. So the plan in reality is simple, because I think every one of us has heard at least a few dozen times in their lives how slow Python really is, and all those benchmarks and those dots flying around where Python is the slowest. I kind of want to show that not only can Python be really fast if you're smart about it, Python can be on par performance with compiled languages even in supercomputing environments. So the quick plan is that I will describe in few words what NumPy does in this project, what MPI does in this project. Then I will describe why we need NumPy and MPI, why does it even exist, and what are the issues of combining NumPy and MPI code in Python. I will then go and talk about a bit about a different project that utilizes NumPy and MPI as its performance driver, which is PyMP data, and that's that. So that's the plan. Okay. So most people probably have heard of NumPy. NumPy is this little thing that allows us to compile Python code to machine code and use those compiled functions, which is super nice, especially when we're doing simulations, which is what I do. It's very nicely integrated with NumPy, so there's never really an issue, mostly. And it's as simple as I said, just adding a decorator, which is visible here, over our function, and it's going to be compiled, uses compiled thing. Okay. So, as a quick intro to MPI, MPI is nothing else than a set of routines that allow us to communicate between different nodes, so different processors, for instance, in a high-performance computing environment, or your home PC if you really want to, but it's kind of slow. And MPI has a very nice, you can have very nice access to MPI calls and MPI routines in Python using MPI for Py. Again, quite simple. The syntax is relatively the same as those C++ libraries. And in this example, we just get some random data, we send it to one processor, receive it on that processor, and that's basically like the basic thing you can do. MPI also offers a lot of more different and advanced routines. For instance, you can do operations while sending the data on the data, so that's very lovely. And before I go further and try to combine those two powerful tools for a very nice computational experience of our lives, we have to do some number crunching. So, using all of this and all those powerful tools for calculation requires to do some calculation. So we have this little integral is equal to pi, which is lovely. And I again forgot if pi is closer to 3 or 4, so I have to calculate. This will be performed. First we were using just number, then we will try to apply MPI and see how bad it goes. Okay, so this is like a simple code to calculate this with like this most naive method of using rectangles, even sums. And if you would run it, I calculated a speed up of about 60 times and just using pure Python. Nice, that's very nice, because all I did was add a decorator. Okay, so I want to go even faster. I want to go above and beyond. So what I did is do another function again. This function will dispatch the task in a distributed memory fashion, and I want to use number because, well, that's the whole idea. I want to compile this and use MPI. Well, I can't. Too bad. Shows up. No. So what happens is number by itself isn't really that great at, well, classes, or rather being passed a random class from Python and compiling it. So what we do is take a different approach, because if we can't really use MPI for Py, we have to do something else. That's where NumPy comes in. NumPy basically takes the pure C API, accesses the C API of MPI, that's a lot of letters, and that's something NumPy can compile. So, we switch up MPI for Py for NumPy, and this code block would calculate Py in a distributed memory parallelism fashion. So, the idea of why we would even want to compile MPI calls is that if we were to just ignore this issue and, well, let Python handle our MPI communication, we would be in a very weird situation where we would go into a JIT compiled block to do some calculations, then we would have to leave to do the communication, and so on and so forth. That wastes a lot of time. A lot. So, with using NumPy over MPI for Py, in cases where we do a lot of calls, MPI calls per calculation, we get even up to 300% speed up. So that's the time we get by not having to just constantly get out of the machine code blocks and having to fall back on Python. And I think that for anyone who would like to do any high-performance calculations with all those nice Python libraries, it's very, very useful to have this option of never having to leave the JIT compiled blocks. So, why is all of this relevant? Well, I do simulations, I do large-scale simulations sometimes, and I want to be able to solve my equations fast, even on very big problems. So, I work with this algorithm called NP-Data, which is focused on solving convection problems. I will not be going into much detail other than that a lot of problems in math and physics can be kind of reduced to this equation, so it's very handy. And PyNP-Data implements this equation along with this little diffusion term, which is visible here, using heavily relying on number for performance, and the way we do this whole thing and how we use both number and MPI would be simply put, we have a grid, because math in the computer is discrete, so we have to have a grid. We have some points on this grid that those are the values we want to calculate. We maybe have some velocities or some momentum that will drive our interaction. And the idea is simple, we just dispatch those tasks, basically. We tell processor 1 to handle one part of the domain, processor 2 to handle this part of the domain, same with threads, which is available thanks to number. That's the simplest idea that starts in this. I ended up MPI on the other hand, because we have to kind of make it a sub-package for certain reasons. Again, relies heavily on the fact that we can use all those processors, all those computational nodes to speed up our calculations, and those images kind of show how in reality this domain decomposition, as we call it, would look. So we have a part of the domain, so this is a third of the domain, which is given to one processor. This processor then has the task of dividing it again further, those will be those dotted lines, and we can do it in any fashion we want. So any direction we want, and achieve something quite nice. Okay, I also wanted to show, before continue with this one. This was taken last time, but I thought good. Okay. Firstly, yes. So this is another example gallery that we have in our documentation, which is nice in itself. So I kind of want to also explain certain issues that arise from using MPI and those kind of things, because really you have to care about how we send the data and when we send the data from one node to another, because, well, this isn't, you cannot like exchange things immediately, as in if you have one wall and the second wall, we could call those walls, this wall between processes, you either have to decide that you go from 1 to 2 first, from the left to the right or right to the left. That's also one issue you have. And you kind of have to decide which direction is correct. It's arbitrary. And then I had one more thought. Yeah. And it's also very important to note that using this kind of a setup where we divide the domain again and again comes at a risk of, well, dividing it too much and actually just slowing us down, because we can throw 100 processors at a problem, but if we get 4x4 grids in the end, which is going to waste a lot of time on communication and not a lot of time on calculation. And the other thing that I want to show is that this is the example gallery of the non-parallelized, as in not MPI library, is that affection, why I'm talking about PyMP data specifically is because affection and convection problems are happening or are describing a lot of things in our world, including fluid dynamics or option pricing, and having this ability to just simply import NumPy and implement it into our calculations quite seamlessly is something I think is worth for anyone who's doing any high performance computing. Not just advection and advection like I do. And I maybe have still too much time. I kind of calculated this whole thing wrong, a bit too fast. So yeah, I guess that would be that. I want to go to my slides back. Oh, okay. And I wanted to thank you for your attention. I don't think I have much more to say other than try out MPI on your own, and I hope you like it.
Great, thank you very much. Do we have any questions? Perfect, okay, all right, well thank you. We're running slightly ahead of time, so feel free to take a little break now, and then the next talk starts at 2:40, talking about Python Philosophy 2.
I'm going to check. Is it that?
Okay.
Working?
That's good.
Excellent.
So yeah, we've got 20 minutes, but we should
it's
wait.
quite a lot of time.
Yeah.
Anyway.
But we want to make sure that people can come from the
Sure,
other
sure,
room
sure,
and
sure.
and
We
learn.
cannot start that. So this is for. I don't think I will need it. Maybe just the pointer, maybe.
Yeah.
This works.
Yeah, it does a little bit.
A little bit.
It's quite bright.
Yeah. Okay. No, I don't think I'm not going to use it.
Cool. We'll get started in a couple of minutes.
Okay, sure.
So I'll introduce you. How do I say your name? Is it Francesc?
Francesc. Perfect. It's not easy. It's not that easy. Did you practice or no?
Again, it was a good guess, I guess. But yeah, so I'll introduce you. I've got some little signs to let you know.
Sure. So I'll hold those up, and then you've got a 20-minute slot. So the way they've been doing it in the other rooms is like 15 minutes for the talk and then 5 for the questions. Do you want that, or do you want the 5 minutes for the? Do you want to do 20 minutes for the talk with no questions?
Probably something in the middle, maybe.
Well, if I
maybe keep 3 minutes for questions.
Yeah, okay, that's fine.
I mean, during my rehearsals, I think I can keep it under 17 minutes or things like that.
Yeah.
Let's see. I can use whatever mic.
Yeah, I'll introduce you and then just pass you the mic if you like. Okay, hello everybody. Welcome to the last talk of this session. I'd like to introduce Francesc, who's going to talk about Python compression with BLOS.
Thank you, Jack. So, I am Francesc Martet. I am the team leader of the BLOS development team, and I am also the CEO of IronArray, which is a company that we are based in Europe. So, what we are going to talk about is first of all a small introduction on how physics law are affecting data science. Then I will continue with how to compress better and take advantage of that for computing bigger. And then I will show a few things about how to share faster with Catalan. So first of all, who is IronArray? So we are developers of Pytables, Numex, and BLOS libraries. And we are a team of experts that can do consulting for companies or research institutions or whatever. Okay, so let's start on how physics laws affect data science. So first of all, you know that the CPUs and RAM and everything is mostly based on transistors, right? The power consumption of transistors, it happens that it's proportional to voltage, to the square of the voltage, and also the frequency, right? In general, you cannot touch voltage too much, okay? So normally you can play with the frequency in order to get faster speeds, right? The problem is that as transistors got smaller, they didn't proportionally reduce their power consumption as expected. And this combined with this dependence in the frequency, have led to this scenario where we can see that frequency is fault in the middle of 2000, sorry. And then we can see that the increase of a single frame performance is not it is not linear anymore, right? So it is scaling, but much more slower. However, the number of transistors in modern CPUs is still increasing following the Moore law. And one of the consequences, so where are putting all these transistors, the manufacturers of CPUs? So normally what they are doing, once they stop to increase the frequency, they started to add much more logical cores, okay, in the same CPUs. So we are in a situation now where we can have, it's very normal to have like 8 logical cores in CPUs, and in servers we can have up to 100. This is becoming more and more normal. So this shift to more transistors, due to the limitations of the power dissipation thing, has led to multiple cores for parallel processing, specialized processing units like GPUs, AI accelerator, dedicated media processors, and then hardware acceleration for specific tasks, for example, Intel Q80 for accelerated compression, and then larger caches to reduce memory bottlenecks. So this is how CPUs look like nowadays. This is Intel Alder Lake, which is 2 years old, and we can see the different cores that we have in the chip. Okay, and especially we can see also the increasingly amount of space that is taking the caches, okay, in the CPU. In this case, it is L3, okay, but we can see also L2 somewhere around here. And this is really, really complex. To make things worse, memory is getting more complex as well, right? So instead of having just a single main memory thing, CPUs normally have different levels of caches internally, right? And these memory caches, you need to be aware that they exist, because if you want to get good performance, every level has different properties. So level 1 is much faster, but it's very small. Level 2 is something in the middle, and L3 is the largest in the CPU, but slower as well. Okay. And efficient access to memory from multi-threaded applications is getting more difficult because interactions among these threads and data. Okay? So when you have different threads, there are different interactions between different caches, and they create coherence problems that makes making things scaling very, very difficult or more difficult. So, for example, this is me trying doing programming multi-thread code and expecting speed ups. So, trust me, it is not fun. It is very, very complex, actually. I think we live in an ironic moment in history, because in one hand, we, and together with LLMs, of course, are producing more code than ever. On the other hand, software is increasingly slow, or, if you want, it is increasingly difficult to get the most of modern CPUs and GPUs, simply because they are much more complex. In conclusion, we are producing suboptimal code at a rate never seen before. Okay. In my opinion, one of the solutions is to stand on the shoulders of efficient libraries. So let me introduce you BLOS 2, which is a container for multi-dimensional binary data. So BLOS 2 is a set of codecs and filters orchestrated in a way that leverages modern computer architecture, and that's important to stress out. It has support for multi-threading, which is critical in nowadays CPUs, It can automatically dispatch and use simple instruction multiple data in modern CPUs, like AVX2, AVX512, Neon, Altivec, a lot. It has also double partitioning. I will explain that very soon, mimicking the multi-level caches that are in modern CPUs, and can adapt automatically to the sizes, and it supports in-memory storage, or in-memory or on-disk storage as well. So it is, BLOS2 is a C library, and on top of that we built the Python wrapper, which is much more powerful. Let me say a few words about the BLOS2 architecture. So you can create 64-bit containers. In the header of these containers, you can have different meta layers that depends on the applications. And then in the section, in the data part, we have different chunks, that these chunks can be split or are split generally in a second partition, which is called blocks. Okay? And then in the driver, there is the variable length meta layers where users can add their own metadata. Here is, for example, a representation of a data set which is made of different chunks, and you can see that these different chunks can be split also in blocks. Okay? And everything is multidimensional. So all these partitioning have multidimensional knowledge, which is important. Okay, so BLOS implements different codecs and filters. If you combine these different blocks and filters and you check and you choose different compression levels, you can get a huge variation on compression ratio, right? So we have here different codecs and different combinations with filters, and we can see that the compression ratio, this is a real data set from climate science, I think. Then we can get from 5x to more than almost 20x. So the thing is how to predict which is the best combination, because sometimes you want better compression, but you have to renounce to speed, and the other way around, you want to be more speed and less compression ratio. And for that, we created BTune, which is a tool to help doing that. But I am not going to explain more on BTune. Let's go with the next section, which is how to compute about the internal compute engine that we have implemented in BLOS2. This compute engine only works on the Python wrapper. Okay, it's not for the C library. So this computing engine is all about computing with compressed data. Okay, in a transparent way. And for optimal speed, it is crucial to understand, which is very important, and also, of course, utilize modern CPU capabilities. So, in this compute engine supports multi-core processing, simple extraction multiple data, and cache hierarchies. Okay? So here's an example of how you can use it from Python. You create 3 data sets, and then you do a reduction like this, and we can use the same functions as NumPy because we override the NumPy universal functions, the universal U functions. Okay, so it's very easy to use. And the interesting thing about it is that this compute engine is very intertwined with the compression engine as well, right? So the idea is that during the computation, not the compressed data touches the main memory, because this will slow down the computation quite a lot. So here's this plot where we see in the x-axis the size in gigabytes of the operands, and here in the y-axis is the performance measured with I/O bandwidth. And we can see that, for example, this is the performance on NumPy that only uses one core, and the temporaries are stored in memory, so that is very bad for performance. Okay, and then we can see that BLOS, the internal compute engine continues to scale very, very well. And the important thing also is that even you can do computations out of core very efficiently. For example, if you do that from disk, you can get still very, very nice scalability during all the process. So BLOS is a good way to do evaluations of expressions that are out of memory. Okay, so let's have a look at something that we have implemented recently, which is called the tree store, which is a way to embed structure in your data effortlessly. So with that, it is possible now to create like a data set that is made of different, a file that is made of different data sets following a hierarchy. And you can see an example here, which is, shows that it's very easy to use, right? You just specify the path, okay? Sorry. And then you assign to a different data set. It is currently in beta, and we are speaking tomorrow on that, so if anyone is interested, please join us. Here's some benchmarks on my laptop, where we can see that for writing and for reading, BLOS2 can be much faster than HDF5 or ZAR, right? And the reason is because we are using multi-threading behind the scenes, things that cannot be done in SciPy or ZAR, by default at least. Then the price to pay is that the average access time is a little bit lower or higher. When we compare with one thread, for example, before it was 8 threads, when we compare one thread, performance is very close in TreeStore and SciPy, for example. Okay, and that means that in all these benchmarks, everybody is using the same BLOS conversion to compare apples with apples. Okay, so for the last part of the presentation, let me introduce Caterva 2, which is a way to bring computation closer where data is stored. So data is equally affected by physical loss. So for example, you try to download something that is in the cloud, which is 100 megabytes, that's easy to do, okay? If it is 100 gigabytes, it's not that easy, but it's still possible. But of course, if you have 100 megabytes, there is no way to do that and processing that in your local computer. So what we did in Iron Array is to bring all this processing and the different tools that the user typically has in the desktop or laptop, so that you can you can compute and analyze your data directly into the cloud. Okay, and then you can share the data with your team, the post-process data. And we are doing that via Caterva 2, which is a client-server application where you can serve different storage and you can process it. And there is a REST API where the user can interact with the server. Okay, and then also the data always flow compressed if it is large. If it is small, like metadata, we use JSON in order to transfer that. Everything is open source. So to conclude, BLOS2 offers a tooling for modern computing, right? So with Python BLOS2, for example, you can do efficient compression and adaptability because it supports a wide range of codecs and filters. And then the fact that the computation is intertwined with compression also allows you to compute bigger. And then with Caterva 2, you can bring all of these advantages to the cloud, okay? And then you can share your data faster. So the idea is that you don't have to worry too much about performance, you can always use the BLOS2 ecosystem and do your thing with the security that all the things that are doing in BLOS2 are leveraging the most modern architectures. So last, thanks to donors and contract. Without them, we couldn't possibly have done the library. And then in the name of the BLOS development team that has put their souls through the years, thanks. And I will be happy to take any questions you may have.
Great, thank you. Right, I'll run around with the microphone if you have any questions.
One question, but I'm curious, what kind of, I mean, if you go back to the slide where you were showing some performance improvement from this reduction, it sort of looked like it had a rather easily compressible input in this case. I'm wondering, how would the numbers change if you turn from this into a more random array of data? Of flows in this case, for example?
Yeah. That's a good question. So random data typically doesn't compress, right? This is why it is random. So the compressors cannot compress random data. And that means that the possible bandwidth savings that you have when you use compression, these advantages doesn't appear when you are dealing with random data. So typically you should expect less performance when you are dealing with random data. But in most cases, in scientific data, there is a lot of redundancies in many sense. This is where compression can actually help. Does that solve the question?
Yeah, but actually, I was wondering if, for example, this had sort of different algorithms or different kind of data that would somehow still be able to find patterns.
Find patterns in random data, you mean? Or?
Yes, sort of like that.
No. Well, it is truly random data. I don't know any codec that can really compress that. It's because it's random, right? So the entropy is really very, very, very big. Okay.
Great. Next question. Is there a hand up over there?
Hi, Francis, and thank you for the talk. I was reading the release notes recently that you're making progress towards supporting the array API, that has been mentioned a few times. Are you tracking this somewhere, or what? How is that in your priorities?
Yeah. So before coming here, our main goal was to try to adapt in a naming. When we were naming methods and functions, we would try to adapt to the API specification, array API specification. And now, after several talks here, I realized that becoming fully compliant with the array API is much more costly. You need to do more things, right? So, probably, and I would like to give high priority to that. And in tomorrow's sprint, we would like also to try to address that. So, if there is someone in the audience that want to join us to make us started on that, I will appreciate that. Okay?
Great, thank you. Well, we're at time now for the session. It's the beginning of the coffee break, so if anybody else has any more questions, I'm sure Francis will be around to catch and ask further things. So yeah, it's a 30-minute break now, and please head back to this room for the next talk, but one final round of applause for
Thank you.
To Cindy. Yeah, because you have like different codecs, and in NumPy we have now Highway, and then we have SciPy.
Cindy is buried in the layers through Numex.
Okay, but Numex.
Can use Intel and KL.
Okay, and then the internal compared to ITVEC and whatnot, you don't specialize in
Yeah, I mean, all the vectorized functions internally, they are
Intel,
Intel.
MKL means the SVML you get also, but
Yeah.
that's just not ITVEC, right? It's just AVX type.
Well, in Conda Forge, or in Anaconda, somewhere is activated.
Probably.
But the user can activate by themselves, by compiling manually as well.
So you don't. So you rely on MKL to provide the assembly implementation.
Yes.
And then I'm surprised that ITVEX also.
ActiveX. No, ActiveX is for the compression.
Only for the compression.
Yeah. So Intel NKL is for is only for Intel.
Yeah. And then you get
Intel
SVML,
CPUs.
and then you have the Intel. Well, I mean,
Yes.
also AVX too, I think.
AVX.
You get also pull out all
Exactly. Even AVX 512, it is implemented by AMD.
Yeah, I was wondering.
Even more spread than Intel.
Because remember we have this universal intrinsic layer like highway and whatnot.
More or less
It's
right.
a mess.
I just
You're trying to outsource this for now for SVML, which this is where we started, right?
Yes, exactly. We started also a path of optimization path for different. You are having like meetings, no? Regular meetings for optimization.
There's some optimization.
it's like the
You don't participate on